A semicircle of radius 2 centimeters with the center at the origin as shown is carrying a steady current of 5 amps. Calculate the magnitude and direction of the magnetic field at 004 centimeters in this coordinate. So we're going to be using Biot-Savart's law to find the magnetic field. So that's dB equals mu naught over 4 pi I dl cross r hat over r squared. So first we're going to find dl. So we defined the radius of our semicircle and theta, and I drew out dl, and that's just the tiny segment that's carrying a current that makes it a semicircle. So this angle right here is 90 degrees. So if that angle is 90 degrees, we have an axis like this. This would be theta. This would be alpha. This would be theta. And this angle is 90 degrees. So this would be theta. And dl is a vector, so it has x and y components. Just looking at this theta right here, the x component would be sine theta. Sine theta, because when we look at the x right here, this, I'm going to use another color just to show you. This is our x right here. This is our hypotenuse. This is our adjacent side. This is the opposite side. So opposite over, sine is opposite over hypotenuse, and that's going in the x direction, so that we get sine theta. And then y would be negative cosine theta, because same, this side in the negative, it's in the negative y direction, and it's adjacent over hypotenuse, so cosine theta, and then z is just 0, because we're only looking at the xy plane, so there's no z. Now we're going to find r hat. R hat is just equal to the r vector over r. So we want to find the magnitude direction of the magnetic field at a point on the z-plane. So our final point is going to be 0, 0, z, minus our initial, I didn't put 4 because we're going to calculate that in the end, and then minus our initial, which is going to be x, y, 0, and just over r. So then we get negative x, negative y, z over r. Now we're going to plug this back and forth with the initial dB equation, and we get mu naught 4 pi I dl, the tiny arc length of that is just rd theta, and then over r cubed because of this r times this r because r cubed. And then we're going to have a matrix for our x and y z coordinates. So we have sine theta, negative cosine theta, 0, negative x, negative y, and z. Okay, solving the matrix, we get x hat negative z cosine theta, because it's negative cosine theta times z, and then we have negative y times 0, that's just 0. And then negative y hat z sine theta times z, and then negative x times 0, 0. And then we have plus z hat negative y sine theta minus x cosine theta, because we have sine theta times negative y, and then negative x times negative cosine theta. It's positive cosine theta, x cosine theta, but then we subtract it here, because that's how you solve for the determinant. And then we're going to actually break this down. Oops. I'll break this down. So this is just going to be negative y hat cosine theta is just going to be y over r minus x cosine theta is going to be x over r. And this just equals negative y squared plus x squared over r, which is just negative r squared over r, which is just negative r. So it'll just be negative r z hat. Okay, so since we solved for the matrix and we got our answers, we are just going to plug that back in to equation and separately solve for the x, y, z direction. So first we're going to do dbx. So dbx is equal to dbx is equal to mu naught over 4 pi I r d theta over r cubed negative z cosine theta. So the magnetic field in the x direction is equal to negative mu naught over 4 pi I r z r cubed integrating from 0 to pi cosine theta d theta. So we took the constant out, negative z, and now we're going to integrate cosine theta d theta. And this is just going to be 0. So the magnetic field in the x direction is going to be 0. Next we're doing dby. dby is equal to mu naught over 4 pi r I r d theta over r cubed, and then negative z sine theta is for the y direction. And then, so by equals negative mu naught 4 pi I r z for r cubed from 0 to pi sine theta d theta. And this would just equal, so sine theta, the derivative of that, is going to be cosine theta. Cosine of 0 is 1. Cosine of negative pi is negative 1, but we're subtracting, it just becomes a plus. So that's just 2. And so we get our answer to be negative mu naught over 2 pi, because 2 cancels on top, and then it becomes 2 on the bottom. And then I r z over r cubed. R cubed is just equal to, since it's just the hypotenuse, it's going to be r squared plus z squared to the power of 3 over 2. So we're plugging in the values of the current, the radius, and the coordinate on the z-axis. So we get by to equal mu naught times 0.04 times 5 times 0.02. We get convert from centimeters to meters, and then 2 pi 0.02 squared plus 0.04 squared 3/2. And we get our value to be negative 0.12 mu naught. Now we're going to find the magnetic field at in our last direction, which is the z direction. So dB z is equal to mu naught over 4 pi IR d theta over r cubed negative r this equals negative mu naught 4 pi IR squared over r cubed from 0 to pi d theta. I don't know if I explained why 0 to pi. Going from 0 to pi because it's a semicircle. That's why we integrate from 0 to pi to find the total magnetic field at that point of interest. And we get negative mu naught over 4 IR squared over r cubed. The pi's cancel because there's going to be a pi on top and then pi on the bottom. And then, as I stated before, r cubed is just equal to r squared plus z squared 3. And then, substituting in our values, we get negative mu naught times 5, 0.02 squared over 4 times 0.02 squared plus 0.04 squared to the power of 3 over 2. And then we get the value to be equal to negative 5.59 mu naught. So the B field is equal to mu naught, x is 0, y is negative 7.12, and then z is negative 5.59. You have to write the magnitude and the phase. So we get the magnitude, if we square this value and this value, square it, add it, and then take the square root, we'll get 9.04 mu naught as a magnitude. And the direction is going to be 52 degrees, and to get 52 degrees, you do tan inverse of negative 7.12 over negative 5.59. And that is the answer for this problem.